So, hello, welcome to the lecture series by Wei Li, and the topic will be the introduction to quiver BPS algebras.
Okay, thank you very much, Piotr, for the introduction. So, for the next 4 days, 5 lectures, I'll give a introduction to the topic of quiver BPS algebras. So I made a rough plan of these 5 lectures. So the first one now will be the overview. So I'll first provide a motivation. Since I understand there will be both mathematician and physicists, so I try to give the motivation from both sides. And then I'll give a rough definition of what we mean by BPS algebras. And then I'll define what we mean by quivers here. And the quiver often come with some potentials. And for the second lecture, which is this afternoon, I'll give a definition of the so this BPS algebra can have different formulations. So for example, you can have a the cohomological Hall algebra, or the VOA, the vertex operator algebra, or Yang-Mian. So this is different types of algebra that can potentially serve as a BPS algebra. And so this afternoon, most of the lectures focus on one particular formulation. And I will explain how this, it turns out to be very general and related to all these other quivers, in particular to the Koha and also to these two for special cases. So I'll focus on this particular formulation. And on Friday, I'll explain how this particular formulation is related to the other ones. So I'll start the definition, and I'll explain some. So this is defined for can be defined for general quiver and super potential, and there's some parts that are universal to all quivers, and there are also some parts that are different for different types of quiver. So I'll explain some classes of quiver that's will be interesting later. So we can have symmetric quivers, and as we'll see that some property depends heavily on what type of quiver that you're considering. And then I'll discuss some examples that we'll see repeatedly later in this week. And then tomorrow so this afternoon I'll just explain this quiver algebra as algebra. And tomorrow I'll try to show that when this quiver algebra is BPS algebra. So for that, we'll need some physics. So I'll first explain the system of equal to 4 supersymmetric quiver quantum mechanics. And then I'll explain some quiver representation theory. Once we have this, we need to understand the BPS spectrum as the representation of the quiver Yang-Mian. So when we look at the representation of this quiver Yang-Mian, there's a special class of quiver, which also the quiver that we first considered when we studied this. So that's the quiver that comes from the toric clubbial threefold. So this type is special in that for this type of quiver, the representation of the quiver Yangnian has some very cute geometric visualization. So the representation can be visualized as some 3D crystals. So one particularly simple example which you might be familiar with is the plane partition. And then once you understand this case, actually once you understand how, so this would be for the C3 case. So once you understand this case, it will be very easy to generalize to the generic toric clubbial 3 case. And then once you understand this, then it'll be very straightforward to see how to generalize to general quiver. So for Friday there'll be 2 lectures. So there are 2 topics. I haven't decided which one to go first. So one is the relation to other formulations. Such as to the Koha, to the OA, and to the Yangnian. And then the last topic will be the application. So one very useful application for this algebra is that you can use it to have an algorithm to count the BPS degeneracies as a character of the algebra. And you can also use this algebra to give some algebraic proof of many relations that you see. So for this, I haven't. So we don't have that much time. So I haven't decided. Actually, this chalk doesn't work well. Like sometimes not. Doesn't stick.
You can have something new from here, but I expect that this is the same kind.
This is better actually. Yeah, this one is better. So I haven't decided which example to explain yet. So I mean, there's some correspondence that involve the BPS sectors, and once we have this BPS algebra, so you can use that algebra to give a algebraic understanding or even proof of those correspondences, and. But to explain the application, sometimes you need other formulations of this algebra. So that's why I haven't decided which one to go first. Maybe I'll just mix them. So that will be the overview. Any questions?
Yeah, maybe I have a question about whether you want to include the preferences of the audience in choosing between different options for this you have in mind.
Yes, definitely. Yes, I will.
Okay, so I can give my vote for Kocha, VOA, and knots and quivers, but please give your voices as well.
Yes, yeah, sure. We'll see. Okay, so let's start here. What's that? So yeah, I wasn't sure how many people in the audience would what kind of background. So I prepared like 5 minutes of 5 to 10 minutes of what is string theory, and I think you don't need to know string theory to understand this algebra. But my own motivation comes from some questions that come from string theory. So, and also later in the lectures, I will use some string theory stuff. So I think I'll just give a short motivation that comes from string theory.
Can I have one request? Now it doesn't matter that much, but can you tell me before you start erasing? This was just a plan, so it doesn't matter, because the quality of the video is not perfect, and I plan to do shots of every blackboard you wrote and attach it to the video so everything will be clear. Hopefully this will work.
Yes, I'm very bad at. I should erase that part first. I know, but yeah, maybe I also erase this part.
Yeah, this I have on my phone.
Preserved for eternity.
Yeah, but I have more students, for example. I want them to watch and learn.
Okay, 5 minutes of string theory. So first and foremost is a theory of quantum gravity. By which I mean that it's a theory that unifies quantum mechanics and general relativity. So it's actually not that easy to have a consistent theory of quantum gravity. So that's why when we have one, we study seriously. And the reason why it's not easy to have one is that when you quantize say the 4D Einstein gravity naively, you get the divergence that you can't remove. The terminology is that the theory is non-renormalizable. So the string theory bypasses this problem because the basic object of string theory is not point particle, but strings. So there can be open strings like this, or they can be closed strings. So the strings are perturbative objects. So there can also be non-perturbative objects, which is we call P brains. So when we say the P brain, so the P is positive integer. So this will have a P plus 1 dimension or volume. And so the D brains are the stuff that the open string can end on. So they provide boundary condition for open string, and also they are dynamical, meaning that they can vibrate. So this is something that we're going to use later. So I think that the fact that the string theory is a consistent quantum gravity is already a reason to study it. But the reason, but if you're a mathematician, I think another very important motivation is that you can use string theory. You can think of string theory as a magical machine that generate dualities. So. So what do I mean by duality here? So I have two theory A and theory B. So if I only consider the the perturbative sector of these two theory, they're not the same. But once you include the non-perturbative sector of both theory, they start to be the same. So this can be very non-trivial. So for example, the ADS CFT, meaning that you have a quantum gravity living in a ADS asymptotic anti-de Sitter space, and this will be completely equivalent to a CFT living on the boundary. So in particular, that means that this equivalence will allow us to use a non-gravitational quantum theory to completely characterize the quantum gravity theory. And another famous example is the M-theory duality web. So I didn't mention that this string theory, you don't just have one, you can actually have more than one type of string theory. For example, and together with the 11-dimensional supergravity, and 2A, 2B, 3B. So this theory has very different low energy descriptions. But when you start to include the non-perturbative sectors, they all become the same. And then they're unified by this M theory that living in the 11th dimension. So, and also there are some basic dualities of string theory, like T duality, S duality, and using them you can generate more and more dualities. So, but you see that the fact that this is non-trivial is precisely give you the it's a reason why it's very difficult to check a duality. If someone tells you something, and you have to include all the non-perturbative sectors in order to check this duality. So that's bring us to this concept of the BPS sectors. So so if your system has a supersymmetry, the states has satisfied a bound. So this is the BPS bound. So so when your states saturate this bound, they are the BPS states. So you see that when you have this BPS, when the states of BPS, that means that they will live in a shortened representation. And this is a discrete statement. That means that when you turn on the perturbation, this condition wouldn't change. So that means the BPS condition is robust against perturbation. So that means that if you give me some duality, I want to check it. So the first thing I want to do is that I want to focus on the BPS sectors. So now in the BPS sector, so normally what people look at is you can look at its index, meaning that you count the states weighted by the signs. So it's the number of bosons minus number of fermions. And then you can look at the correlation function of the BPS sectors. And in this series of lectures, I want to focus on the algebraic structure of the BPS sectors. So now I want to explain what we mean by BPS algebras. So first I want to emphasize that when people say BPS algebra, it's not just a symmetry algebra of the BPS sector. I mean, it is that, but it's not just. It's much more than that. It's algebra of the BPS states. I think this chalk, once you use it for a bit, it doesn't start to So by this algebra of the BPS state, so this is the definition that's given by this paper of Hagen in 1996. So roughly speaking, the elements of this algebra would be the BPS states. So let's call this BPS Hilbert space, and the multiplication of the algebra will be some kind of fusion process. So you take two BPS states and then you bring them together, and then you get a third BPS state. So the whole point of defining this algebra is to specify what you want to include in the BPS states. I mean, it can be not just the local operators. You also want to have you can also put defects, and so you want to specify this. And then also you want to define precisely what you mean by fusion here. Can I erase?
Yes.
I think over the years there have been some studies of this BPS algebra that people actually didn't say clearly that explicitly that this is BPS algebra. I mean, sometimes people will see some dualities or correspondences, but which is actually the reason there is this correspondence is because there is a BPS algebra. So that's why there can be more than one possible formulation of this algebra. So the formulation I want to start is the so-called quiver-Yangian. So starting from there, I can then try to relate to the cohort. So this will be roughly by some positive subalgebra. Meaning the subalgebra that's generated by the racing operators, and this would be the equivariant version of the spherical cohort. So this is the most these are both defined for general quiver and superpotential, and I think this cohort can be actually more general. And for some special cases, so this will reduce to the ordinary Yangian. And also, when the quiver is some special quiver, it will become isomorphic to the universal enveloping sum algebra of the VOA. So now I think that for 15 minutes, so I'll explain quiver and potential. So, any questions so far? A quiver is just a duality graph. There's two pieces of information. So it has a bunch of vertices, and the set we'll call Q0, and then a bunch of arrows that connect these vertices, and we'll call them Q1. And let's define. Let's use this notation to denote the set of arrows that go starting from that go from B to from A to B, and this means I use this notation to denote the number of arrows of from A to B. So and we also define symmetric quiver, meaning that any pair of vertices in Q0, the number of arrows from A to B is equal to the number of arrows from B to A, and the non-symmetric quiver or chiral quiver is otherwise. So the simplest quiver, so example. So the simplest case is just one vertex with no arrow, and then we can have one. So I normally label the vertex from 0, 1. Or sometimes people label from 1. Doesn't matter. So you can also have a vertex with just one arrow. So this is called Jordan quiver. Or with loop quiver. Or you can have two vertices with some arrow going this way, some arrow going back. So this is all or like this. So this is all symmetric. So this loop quiver will be the building blocks for all the quiver that appears in this not quiver correspondence. So the simplest chiral quiver you need to have two vertices. Say in this case. So this is OB. So this will be the BPS quiver in the 40N2 algebra series, the simplest one, the A2 quiver. And you can also have arrows. So all this is just a quiver. So now you can also have the superpotential. So the superpotential is a sum of some monomial of the arrows. So for each, so you can have loops in the quiver, and then for each loop, you can have a product of the arrows that's along this loop. And I put a trace here, meaning that it's a cyclic. So it doesn't matter where the so this order is a cyclic. And so an example that will be used for later is this 3-loop quiver with potentials. So it's called superpotential is because this is the superpotential in the for quantum mechanics, and this will give you the F-term constraints. Meaning for the
I have a question. What are these eyes in this context?
it's the arrow here.
Okay.
Here because there's only one node, so I didn't write. I mean, with this notation, I would write 0 to 0. 0.
What does taking the trace over the arrow means?
Yeah, I just mean that here, I mean, in the superpotential, you actually have this trace because each of this I correspond to a bifundamental field.
Okay,
matrix.
okay.
So you're taking the trace. But abstractly, it just means that the order is only up to cyclicity. Okay.
Please wait before erasing.
I think now it's actually natural point to stop.
We can stop now and resume in 1 hour and a half, a little bit earlier.
Or let me just give you more examples. So this is all the examples for the symmetric quiver with no superpotential, and this is the chiral quiver for the. So this is the M conical quiver, and you can have like A2 quiver here. So this is the a symmetric quiver with a non-trivial potential, and so this will see that you rise as the BPS quiver of the type 2A on C3. So you can instead of C3 you can consider general toric club C3. And so here there are two big classes. So you can consider the case without compact force cycle. So this case these are the easy ones. So that means all the quivers coming from this class, they are symmetric. And the difficult ones are this is without compact force cycle. And the difficult ones are the case with a compact force cycle. So this will be the chiral quiver. So this case also has a property that they all isomorphic to some matrix standard W algebras. And so let me draw an example of this one. So this will correspond to the case of type 2A. Instead of on C3, you'll be on C3 mod Z3. So we have, instead of one vertex, we have 3 vertices, and then also 3 arrows. So now you also have a non-trivial superpotential. So it'll be I, J, K. So the deal of the toric diagram will be like this. So you see that there's one compact force cycle here. Any questions? I think now is a natural place to stop. From next lecture, I'll give the definition of the algebra itself. So maybe I'll just. There's no question.
That is for n equal to 4 supersymmetry, right? Single loop.
Yes. So generically, if you consider toric club threefold, then you have and then you look at the volume theory, that will have n equal to 4 supercharges. But you can have when the club is more symmetric, you can have symmetry enhancement. So this one actually has 4 times of the supersymmetry in general. So generically, it's 4 subsets. So this particular case actually has 16. And in this compact force cycle, so if you have this class. In this class, the toric club LC without compact force cycle, there's a subclass, and that's like this. So this one has 8 supersymmetries. But 4 is a generic, is a number for the generic case.
Okay, are there other questions? If not, let's thank Wei for the first lecture. I'll stop recording.